Welcome, everyone. I'm excited to kick off our presentation today with a focus on the fascinating world of multithreading. Today's topic is Chapter 5, Multithreading Concept, part of our Advanced Programming series. Over the course of this session, we'll explore the fundamental ideas behind multithreading, how it enhances programming, and some key concepts to help you understand and implement it effectively. Let's get started. Let's take a closer look at the contents of this presentation. First, we'll start with introductions to threads. Understanding what threads are and how they function is fundamental to grasping concurrent programming. Then, we'll move on to creating a thread, which involves the practical steps to initiate and manage threads within your applications. Next, we'll discuss thread scheduling, which covers how the operating system manages the execution of multiple threads to ensure efficiency and responsiveness. Following that, we'll explore synchronization, a crucial concept that helps us coordinate threads to prevent conflicts and ensure data integrity. Finally, we'll cover the object monitor, which is a key mechanism for controlling thread access to shared resources. Each of these topics builds on the previous ones, forming a comprehensive overview of thread management and control in programming. The human body is a fascinating example of how multiple operations can happen at the same time. For instance, we can breathe, have our blood circulate, digest food, think, and even walk all at once. It's like a busy, well-coordinated machine. Now, while our minds can handle several tasks simultaneously to some extent, it's actually quite challenging for us to switch rapidly between different trains of thought. For example, trying to read 2 or more books at the same time is pretty difficult. Our brains aren't naturally suited for doing multiple complex things at once in this way. This is where the concept of multi-threading in programming becomes so useful. Just like our bodies can perform many activities at once, programs can be designed to perform different tasks concurrently. This means that a program can handle multiple operations at the same time, making it more efficient and responsive. So, understanding how the human body and mind handle parallel tasks helps us appreciate why multi-threading is such a powerful technique in software development. It allows programs to be more like us, capable of juggling multiple activities smoothly and effectively. So, what exactly are threads? Well, to understand that, let's first think about processes. Processes are independently running programs, and they're isolated from each other, meaning each process operates in its own separate space. Now, threading is a way to allow multiple activities to happen simultaneously within a single process. It's like having several tasks running at the same time inside one program, making it more efficient and responsive. Interestingly, Java was the first programming language to explicitly include threading directly within the language itself, which was a big step forward for concurrent programming. Threads are often called lightweight processes because they share many resources but still function as separate paths of execution. Each thread has its own stack, which is like its personal workspace, its own program counter to track where it is in execution, and its own set of local variables. This setup allows each thread to operate independently within the process. However, unlike separate processes, threads within the same process are less insulated from each other. They share important resources like memory, file handles, and other process-wide states. This shared environment can be powerful because it allows threads to communicate easily, but it also means we need to be careful to avoid conflicts or data corruption. So, in the bigger picture of programming and system efficiency, understanding threads helps us create more responsive and efficient applications by handling multiple tasks at once within a single process. So, what are threads? Well, as I mentioned earlier, a process can support multiple threads, and these threads seem to run simultaneously and independently from each other. This means that within a single process, multiple tasks can be happening at once, giving the illusion of parallel execution. When we talk about more than one thread or program running at the same time, that's called multi-threading or multiprogramming. It's a powerful way to improve performance and responsiveness. Another key point is that multiple threads within a process share the same memory space. They can access the same variables and objects, which makes communication between threads more efficient. They also allocate objects from the same heap, meaning they work within the same memory resources. This shared environment is what makes multi-threading both flexible and a bit complex to manage. In Java specifically, every program starts with at least one thread, the main thread. But the Java Virtual Machine, or JVM, also creates additional threads behind the scenes. These are mostly invisible to us but are crucial for the JVM's internal tasks, such as garbage collection and other housekeeping activities. These background threads help keep the JVM running smoothly without us having to worry about them. Beyond the JVM, other parts of the Java ecosystem create their own threads. For example, the AWT and Swing UI toolkits spawn threads to handle user interface events. Servlet containers, application servers, and RMI also create threads to manage network requests, database connections, and remote method calls. All of these threads work together to make Java applications responsive, efficient, and capable of handling multiple tasks simultaneously. So, in essence, threading is at the heart of Java's ability to do many things at once, making our applications faster, more responsive, and more scalable. Let's talk about why using threads can be so beneficial. One of the main reasons is that they allow us to take advantage of multiprocessor systems. This means we can run multiple tasks in parallel, making our applications much more efficient. Another key point is that threads can help simplify modeling. Instead of dealing with complex, monolithic processes, we can break things down into smaller, manageable threads that work together seamlessly. Threads are also great for performing asynchronous or background processing. For example, you can run a task in the background without interrupting the main flow of your application, improving responsiveness. Finally, they enable us to handle multiple client connections simultaneously. This is especially important in networked or server applications, where serving many users at once is essential. All of these reasons really tie into the overall theme of making our programs more efficient, responsive, and scalable through multi-threading. Let's talk about a common problem with single-threaded applications. When a task takes a long time to complete, it can block everything else from happening, which leads to poor responsiveness. Imagine waiting for one big task to finish before you can move on to the next. That's the limitation here. Now, with multi-threading, we can distribute tasks across multiple threads. If you have multiple processors available, these threads can run truly concurrently, meaning several tasks are happening at the same time. This makes the application run more efficiently because it's not waiting around for one task to finish before starting another. But even on systems with just one processor, multi-threading can help. When one thread is busy waiting for something like an I/O operation, say, reading a file or fetching data from the network, another thread can step in and make productive use of the processor. So, in essence, multi-threading helps us make better use of available resources, whether we have multiple processors or just one, improving overall performance and responsiveness. Now, let's talk about thread risks. While Java's thread facilities are really user-friendly, there are some pitfalls you should watch out for when creating multi-threaded programs. One of the biggest issues arises when multiple threads access the same data item. If they don't coordinate their access properly, you might end up with inconsistent or unexpected results. Java helps us manage this with two key keywords: synchronized and volatile. These are essential tools for ensuring that shared data remains consistent across threads. But here's the catch. If you're using synchronization to protect shared variables, you need to be consistent. That means applying synchronization everywhere in your code where the variable is accessed. Failure to do so can lead to tricky bugs that are hard to reproduce and debug. So, in the context of our overall theme of writing robust multi-threaded applications, understanding these risks and how to mitigate them is crucial. Proper coordination and careful use of Java's synchronization tools help us avoid data corruption and ensure our programs run smoothly. All right, let's talk about the thread lifecycle. A thread can go through several different states during its lifetime, and understanding these is key to managing threads effectively. First, we have the newborn state. When we create a thread, it starts in this state. At this point, it's just been instantiated. It exists in memory but hasn't started running yet. Think of it like a newborn baby. It's ready but not doing anything. To move it into the running mode, we call the start method. That's what kicks off the thread, allowing it to begin execution. Conversely, if we want to stop a thread, we can invoke the stop method, although it's worth noting that stop is deprecated for safety reasons in modern Java programming. Next, we have the runnable state. Once a thread is started, it enters this state. It's ready and waiting for its turn to run, essentially queued up and waiting for the CPU to allocate time to it. Here's an important point. When a thread is in the runnable state, it's not necessarily actively executing, but it's prepared to do so. If needed, we can give control to another thread by calling the yield method. This method hints to the thread scheduler that it can pause and allow other threads to run, which helps us manage thread priorities and overall application responsiveness. So the key takeaway is that the thread's lifecycle moves from being created to being ready and waiting, and then to running or waiting, depending on the control flow. Understanding these states helps us write more efficient and predictable multi-threaded applications. Now let's continue exploring the thread lifecycle, focusing on the running state. When a thread is in the running state, it means it's actively executing its task because the CPU is currently allocated to it. Think of it as the thread being in the driver's seat, controlling what happens next. However, a thread doesn't stay in this state forever. It can transition in a few different ways from running mode. Next, we'll look at the blocked state. A thread enters this state when it's not allowed to move into the runnable or running states. Essentially, it's waiting for some condition to be met, such as resource availability or a specific event. Common scenarios include when a thread is waiting, suspended, or sleeping. In other words, it's temporarily paused, unable to proceed until certain conditions are satisfied. Finally, let's discuss the dead state. This is the end of a thread's life cycle. Once a thread has completed executing its run method, its life cycle concludes and it enters the dead state. Sometimes, if needed, we can explicitly kill a thread by invoking the stop method, which forces it into this dead state. Understanding these states helps us manage threads effectively and ensures our applications run smoothly by controlling their life cycle properly. Let's continue our exploration of the thread life cycle. On this slide, we'll discuss some additional key points that deepen our understanding of how threads behave in a system. First, it's important to recognize that threads go through several states during their life cycle, including new, runnable, running, blocked, waiting, timed waiting, and terminated. Each of these states plays a crucial role in managing how threads execute and share resources. For example, when a thread is in the blocked or waiting state, it's typically waiting for a resource or a condition to become available, which helps prevent conflicts and ensures smooth operation. This transition between states is vital for efficient multitasking and resource allocation. Understanding these states helps us grasp how threads are managed by the operating system, ensuring optimal performance and responsiveness of applications. Connecting this to the overall theme, managing thread life cycles effectively is key to building robust, high-performance software systems. It's all about orchestrating threads in a way that maximizes efficiency while minimizing issues like deadlocks or resource starvation. Let's take a closer look at some of the key methods used to control thread behavior. First up is the start method. This method is crucial because it makes the thread runnable, meaning it's ready to run. But it's important to remember you can only call start once on a thread. Calling it multiple times will cause an error. Next, we have the run method. This is where the thread begins its life. When a thread is started, the code inside the run method is what executes. Think of run as the main activity of the thread. Then there's the stop method, which is used to terminate a thread. When stop is called, the thread is essentially being shut down. It's no longer active. Another useful method is yield. When you call yield, it causes the thread that's currently running to pause temporarily. This gives other threads of the same priority a chance to run. It's a way to promote fairness among threads. Finally, we have the sleep method, which can be called with either one or two arguments. When you specify sleep m, the thread pauses for m milliseconds. If you include nanoseconds as well with sleep n, the thread sleeps for m milliseconds plus n nanoseconds. This is helpful when you need precise control over timing in your multi-threaded applications. All these methods give you various ways to manage thread execution, ensuring your applications run smoothly and efficiently. Let's explore how we can create threads in Java. There are two main ways to do this. The first way is by extending the thread class itself. This approach involves creating a new class that inherits from thread and then overriding its run method. The second way is by implementing the runnable interface, which provides more flexibility, especially when your class already extends another class. Now, to illustrate this, let's look at an example. The sample program here is designed to find out which thread the JVM is using to execute the statements. When we run this code, it first prints a message indicating we're about to find the current thread. Then, it retrieves the current thread using thread and stores it in a variable. Next, it prints out details about this thread, its reference, name, priority, and whether it's alive. You'll notice that the output shows the thread is named main, which is the default thread name for the primary thread executing the main method. Its priority is 5, which is the default priority, and the thread is indeed alive during execution. The key takeaway here is that understanding the current thread helps us manage and control thread behavior effectively. This example ties back to our overall theme of thread creation and management in Java, giving us a practical glimpse of how the JVM handles threads during program execution. Now, let's talk about creating threads by extending the thread class. This is a common technique in Java for implementing multi-threading. Essentially, what we do is create a normal class that extends the built-in thread class. Once we have our class extending thread, we override the run method. This is key because the run method contains the code that we want the thread to execute. Think of it as defining what the thread will do when it runs. After overriding run, we create an object of our custom class. Then, to start the thread, we simply call the start method on that object. This triggers the thread to begin execution, executing the code inside the run method. So to summarize, by extending the thread class, overriding run, and calling start, we can easily create and execute threads. This approach makes it straightforward to define thread behavior directly within a class, which is quite useful when you want a clear, organized way to handle multi-threading in your applications. All right, let's dive into creating a new thread using the MyThread class. First, you define your class by extending thread, which means your class inherits all the capabilities of a thread. Inside this class, you'll implement the run method. This is where you put the code that should execute when the thread runs. Think of run as the thread's main activity. When you're ready to start the thread, you instantiate your MyThread object with new MyThread. Then, to actually kick off the thread, you call the start method on that object. This is a crucial step because start is what creates the new thread and then calls the run method internally. So, in summary, creating a thread involves defining a class that extends thread, implementing the run method with the thread's task, and then instantiating and starting that class with start. This process is fundamental to managing multiple tasks concurrently, which is a core theme of multi-threading in Java. Let's take a closer look at this example. Here, we have a class called ThreadDemo that extends thread, meaning it's a custom thread class. In the main method, we create an instance of ThreadDemo and call start on it. This is key because calling start actually begins a new thread of execution, which then runs the run method. Inside run, we print a message indicating that it's from a thread, and then we put the thread to sleep for an hour or 3,600 seconds. It's important to note that after starting the thread, the main program continues immediately and prints its own message. So the output shows both messages. First, the main program's message, and then the thread's message. This demonstrates how threads enable concurrent execution, multiple things happening at the same time. Also, there's a try-catch block around sleep to handle interruptions, which is good practice. If the thread gets interrupted during sleep, it catches the exception and prints interrupted. This example highlights the basic structure of creating and starting a thread and how the output reflects concurrent execution. It connects to our overall theme of understanding multi-threading by showing how threads run alongside the main program. Let's go over a few important things to keep in mind about this program. First, this program will run, or rather sleep, for about an hour after printing those initial messages. So, if you want to stop it earlier, you'll need to press Ctrl-C to terminate the program. Next, it's key to understand that there are actually two threads running in this program. The first one is the main thread, which executes all the statements inside the main method. The second one is a subthread that gets launched by the tstart command. If you look at the console output, you'll notice the order of the messages. It shows us that the subthread took a little longer to start executing its first statement after it was launched by the main thread. This is a common behavior because threads don't necessarily start executing immediately. Another important point is that a multi-threaded program won't terminate until all of its threads have finished executing. This means the main thread and any subthreads need to complete before the program fully ends. Finally, I want to highlight that the run method in the thread class is empty by default. So if you want your thread to do some work, you need to override the run method and put your code there. This is how we define what each thread actually does during its execution. Now let's take a closer look at this example of creating threads by extending the thread class. Here, we have two classes, A and B, both extending thread. In each class, we override the run method, which is the entry point for the thread execution. Inside the run method, we start by printing a message indicating the start of the thread, like thread A or thread B. Then, we have a simple loop that runs 5 times, printing out the current value of I along with a message indicating which thread it's from. Finally, each thread prints an exit message, signaling that it has finished executing. This example is great because it clearly shows how to define and run multiple threads by creating classes that extend thread, and then overriding the run method to specify what each thread does. Remember, when you start these threads using the start method, they run concurrently, which is key to achieving multitasking in Java. This example ties into our overall theme of understanding how threads operate and how to manage multiple tasks efficiently in Java. Now let's take a closer look at this example to understand how threads work in practice. Here, we have a class called demo with a main method. Inside it, we create 2 objects, one of class A and one of class B, and we start each of these threads by calling their start method. When we do this, each thread begins executing independently. Notice what happens when thread runs. It outputs messages indicating its progress, from thread I equals 1 all the way to from thread I equals 5. Before printing exit from A similarly, thread B does the same. It outputs its own sequence of messages and then exits. Finally, the main thread prints end of main thread. But here's the key point. The output from threads A and B can appear in any order when you run the program. Sometimes it might finish before B, or they might interleave in unpredictable ways. This is because threads run concurrently and independently, each executing whenever it gets a chance to do so. This randomness in output highlights a fundamental concept. Threads are not sequential. They run independently of each other, which means their execution order is not guaranteed. This is essential to understand because it impacts how we design multi-threaded programs. The fact that the same program can produce different results on different runs illustrates the dynamic nature of thread scheduling and execution. Now let's talk about implementing the runnable interface. In this approach, we start by defining an interface named runnable. The idea here is that we implement this interface in a class to create a thread. So first, you create a class that implements runnable. Then within this class, you override the run method, which contains the code you want your thread to execute. Think of run as the task that your thread will perform. Next, you need to create an object of that class, the one that implements runnable. After that, you also create an object of the built-in thread class. Here's the key step. You pass your runnable object as an argument to the thread constructor. This way, the thread knows what task to run. Finally, to start the thread, you call the start method on your thread object. This method kicks off the execution and calls your run method internally. This approach is particularly useful because it allows your class to extend from other classes if needed, since you're only implementing an interface. So in summary, implement runnable, override run. Create your objects, pass the runnable object to a thread, and then call start. It's a clean and flexible way to create threads in Java. In this example, we see a simple way to create and run a thread in Java. The class threadRun implements the runnable interface, which means it needs to define the run method. Inside the main method, we instantiate an object of threadRun, then create a new thread, passing that object as the target. When we call tstart, the thread begins executing, running the code inside the run method. What's interesting here is that the main program continues immediately after starting the thread and prints its message, "Hello World," from the main program. Meanwhile, the thread itself prints its own message, "Hello World," from a thread. This demonstrates how threads run concurrently with the main program. The run method also contains a try-catch block, where the thread sleeps for an hour, specifically 1,000 milliseconds times 60 seconds times 60 minutes. This pause simulates some long-running task. If the thread gets interrupted during sleep, it catches the interrupted exception and prints interrupted. This example highlights key concepts: how to create a thread by implementing runnable, starting it with start, and understanding that threads run independently, allowing multiple tasks to proceed simultaneously. It's an essential foundation for managing concurrency in Java, connecting back to our overall theme of effective multi-threading. Let's take a closer look at how this program behaves. It behaves similarly to the previous thread demo program that we looked at, which was created using thread objects with thread subclasses. However, in this case, our thread object T is created with a special constructor that takes a runnable object as input. Since our class no longer extends the thread class directly, we need to call the sleep method explicitly by prefixing it with the class name, thread. This is an important distinction because, when not extending thread, the sleep method isn't inherited automatically. Now, comparing the two techniques, implementing runnable versus extending thread, implementing runnable involves a few extra steps. First, you need to create an object of the class that implements runnable, and then pass that object as an argument to the thread constructor. Additionally, since the class isn't a thread itself, you have to call thread sleep explicitly whenever you need to pause the thread. On the other hand, extending thread is simpler because you can directly call sleep without prefixing it with thread. But there's an important design consideration here. Java doesn't support multiple inheritance of classes. So, if your class needs to inherit from another class, it's better to implement runnable rather than extend thread. This approach gives you the flexibility to inherit from other classes while still creating threads. In summary, implementing runnable is a bit more involved, but it offers greater flexibility, especially when you need to extend other classes. Extending thread is more straightforward but less flexible in terms of inheritance. This choice depends on your specific needs and the overall design of your program. Now, let's look at what happens when we run this program. First, you'll notice that the output starts with end of main thread. This shows that the main thread has finished executing its code, but the program itself continues because the other thread we created is still running. Next, you'll see inside xthread, which indicates that the run method of our thread has started executing. From there, the thread prints out from xthread I equals, followed by numbers 1 through 10, showing the loop in action. Finally, the thread prints exit from x, marking the end of its execution. One key point here is that thread execution is concurrent, meaning the main thread and our x thread are running at the same time. This is why the main thread's message appears first, but the output from the x thread can appear before, after, or interleaved with other messages. This example illustrates how creating and starting a thread allows parallel execution, which is essential for building responsive and efficient programs. In the context of our overall theme, it highlights the importance of understanding thread behavior and how to manage multiple tasks simultaneously in Java. So, it's important to understand that a thread doesn't actually start executing until another thread explicitly calls the start method on the thread, object for that new thread. This is a crucial point because it highlights how thread creation and initiation are controlled in Java. Now, when does a thread end? There are three main ways. First, it simply reaches the end of its run method, completing its task naturally. Second, if an exception or error occurs that isn't caught within the thread, it will terminate unexpectedly. And third, although deprecated, if another thread calls the stop method, it can abruptly halt the thread. An interesting aspect of thread management is that once all the non-JVM threads in a program finish, the program itself will exit. This means that the JVM keeps running as long as there are active user threads. To help manage thread execution, Java provides the join method within the thread API. This allows one thread to wait for another thread to complete before proceeding, which is especially useful for synchronizing tasks. Overall, understanding these points helps us control thread lifecycles better and ensures our programs run smoothly and efficiently. Let's talk about thread priority in Java. Each thread in Java has its own priority, which plays a crucial role in determining the order in which threads are scheduled for execution. Think of it like a ranking system that the thread scheduler uses to decide which thread to run next. Now, if you have multiple threads with the same priority, Java treats them equally. They don't have a strict order among themselves, so the scheduler applies a first-come, first-serve, or FCFS approach. This means the thread that arrives first gets the turn first, among the threads with identical priorities. You can also set the priority of a thread explicitly using the setPriority method. For example, you write thread name setPriority and pass an integer value. This value ranges from 1 to 10, where 1 is the lowest priority and 10 is the highest. Java's thread class provides some predefined constants to make this easier. Min priority is 1, representing the lowest, is 5, which is the default, and max priority is 10, the highest. By default, when you create a thread, it starts with this normal priority of 5, but you can change it as needed to influence the scheduling behavior. Understanding thread priority helps us manage how threads compete for CPU time, especially in complex applications where controlling execution order can improve performance and responsiveness. When we talk about scheduling, it's important to understand that, aside from specific methods like thread join and object wait, the timing of thread execution is generally non-deterministic. This means that the JVM doesn't guarantee exactly when a thread will run, leading to a sort of round-robin scheduling approach. In round-robin scheduling, threads of the same priority take turns executing, each getting a slice of processing time in a fair, cyclic order. Now, a key point here is that the Java virtual machine can interrupt, or preempt, a lower priority thread to allow a higher priority thread to run. This preemption ensures that more important tasks can get CPU time when needed, which is crucial for responsiveness and performance. Connecting this to the broader theme, understanding how thread scheduling works helps us design more predictable and efficient multi-threaded applications. It highlights why managing thread priorities and synchronization is so vital in creating robust programs. Let's talk about sleeping in threads. The thread API gives us a sleep method, which is really useful for pausing a thread's execution. When you call sleep, the current thread enters a wait state until either the specified amount of time has passed or the thread is interrupted by another thread. Now, if the time elapses without interruption, the thread becomes runnable again and goes back onto the scheduler's queue, ready to continue execution. But what happens if the thread gets interrupted? Well, in that case, it throws an interrupted exception. This is a helpful way for the thread to recognize that it was awakened prematurely by an interrupt, rather than simply waiting for the timer to expire. Another method worth mentioning is thread yield. Unlike sleep, which pauses the thread for a specific duration. Yield just temporarily pauses the current thread to give other threads a chance to run. It's a way of being polite in multi-threaded environments. It's important to note that in most implementations, when a higher priority thread calls yield, lower priority threads typically won't run until the higher priority thread finishes or yields again. This helps us understand thread scheduling behavior and how to manage thread execution flow effectively. Let's talk about daemon threads. You might have heard that a Java program exits when all of its threads finish running, but that's not the full story. What about those hidden system threads, like the garbage collection thread or other JVM-created threads? We can't really stop these threads. They keep running in the background. So if these system threads are still active, how does a Java program ever actually exit? That's where daemon threads come into play. These system threads are called daemon threads. The key point is that a Java program will only exit when all of its non-daemon threads have completed. As long as there's a non-daemon thread running, the JVM stays alive. Any thread can be turned into a daemon thread. You do this by calling the threadSetDaemon method on the thread. You might find it useful to set certain background tasks, like timer threads or deferred event threads, as daemon threads, because they only need to run while there are other non-daemon threads active. Once those are all finished, the JVM can shut down cleanly. This concept helps us understand how Java manages its lifecycle and ensures that background or system threads don't prevent the program from exiting when it's supposed to. Sharing variables is a fundamental concept when working with multiple threads in a program. For threads to be truly useful, they need a way to communicate or share their results with each other. The simplest method to achieve this is by using shared variables. However, sharing variables introduces some challenges, one of which is the race condition. A race condition happens when multiple threads, running asynchronously, access the same object, what we call a shared resource, at the same time. This can lead to unpredictable and incorrect results. For example, imagine two threads working with the same file, one reading from it while another writes to it. Without proper control, these operations can interfere with each other, causing data corruption or errors. The way to prevent these issues is through synchronization. By synchronizing the threads that access shared resources, we ensure that only one thread can modify or read the resource at a time. This way, we avoid race conditions and keep our program running smoothly. Overall, understanding how to share variables safely is key to building reliable multi-threaded applications. Let's look at an unsynchronized example to understand the problem better. The main issue when multiple threads share the same data set is that one operation in one thread can interfere with another operation happening simultaneously in a different thread. When this occurs, the outcome can be undesirable or even incorrect. To make this clearer, imagine a bank application with multiple threads, each representing an ATM connection. Suppose you have a savings account with a balance of $100. Now, picture you and your friend trying to withdraw $50 at roughly the same time from two different ATMs. What do you think might happen? If those threads run independently without any coordination, both of you might end up receiving $50, leaving the account with only $50. But in reality, the bank would lose $50 because both withdrawals are processed as if there was enough money, even though there was only $100 initially. This kind of problem highlights why synchronization is so important. By coordinating access to shared data, we can prevent these conflicts and ensure the integrity of the data. So, the key takeaway here is that without synchronization, concurrent operations can lead to inconsistent or incorrect results, which we definitely want to avoid in critical systems like banking. Let's talk about synchronization, specifically about locking an object. In a multi-threaded application, synchronization is crucial because it ensures that when one thread is updating shared data, other threads wait and see the most recent value. Without this, we could end up with inconsistent or corrupted data. Synchronization works by using a lock, which essentially represents the shared data. Each thread can check the lock's status to determine if it can access the shared resource or if it needs to wait. This way, threads coordinate their access and prevent conflicts. Now, when we write synchronized code, we do so in what's called a synchronization code block. This block is a segment of code within a thread that requires exclusive access to a particular lock. Only one thread can execute that code block at a time, which preserves data integrity. However, it's important to remember that more locks or longer synchronization blocks can impact performance. They can slow down the application because threads spend more time waiting for locks to become available. So it's a balance, using synchronization effectively without overly hindering performance. Let's talk about synchronization, specifically locking an object. Synchronization is a key technique in concurrent programming that helps us manage access to shared resources. It involves three main elements. First, there's the lock itself. Think of it as an object that can be in one of two states, locked or unlocked. When it's locked, it means some thread is currently using the resource and other threads need to wait. When it's unlocked, the resource is available for use. Next, we have the synchronized block. This is a section of code that we designate to run with exclusive access. It's associated with a specific lock, meaning only one thread can execute this block at a time for that lock. Now, the core rule here is what happens when a thread encounters a synchronized block. The thread checks the associated lock. If the lock is already locked by another thread, the thread will wait, pause its execution until the lock becomes available. If the lock is unlocked, the thread proceeds to execute the synchronized block. Once the thread finishes executing the lock is released, unlocked, making it available for other threads. This ensures that two synchronized blocks that share the same lock will never run simultaneously. This mechanism is fundamental to maintaining data consistency and avoiding conflicts in multi-threaded environments, which ties directly into our overall theme of writing safe, efficient concurrent code. Let's explore how Java supports synchronization. Instead of leaving it entirely up to programmers to create their own locking mechanisms and manage synchronization blocks, Java simplifies this process. It provides a built-in synchronization monitor on each instance of the object class, which means that object can be used directly as a lock. Since every class in Java is a subclass of object, this effectively makes all objects in Java capable of serving as synchronization locks. Additionally, Java offers 3 different ways to define synchronized blocks, giving developers flexibility in how they implement thread safety. This design helps make concurrent programming more intuitive and less error-prone, fitting neatly into Java's overall approach to managing complex processes efficiently. So let's talk about how Java supports synchronization, starting with one of the main ways, synchronized class methods. When we define a method as static synchronized, it means that the entire method becomes a synchronized block. In other words, only one thread can execute that method at a time for the class. The lock used here is the class object itself, not an instance. This is particularly useful when you want to ensure that no two threads execute that static method simultaneously, maintaining thread safety at the class level. This approach is a straightforward way to control access and prevent race conditions in shared resources or critical sections of your code. It ties into the overall theme of Java, providing robust tools to manage concurrency effectively. So let's talk about how Java supports synchronization, specifically through the second way, synchronized instance methods. When you declare a method as synchronized, like this, it means that all the statements within that method become part of a synchronized block. And the key point here is that the lock used is the instance object itself. So when a thread calls this synchronized method, it acquires the lock on the specific object instance, ensuring that no other thread can execute any synchronized method on the same object simultaneously. This is a very straightforward way to control access to critical sections tied to particular object instances, which helps maintain thread safety without much fuss. It's an elegant way to ensure that only one thread can modify or access shared data at a time, aligning perfectly with Java's overall approach to safe concurrent programming. Let's take a closer look at how Java supports synchronization through the synchronized statement. In this approach, you define a synchronized block inside a method using the syntax synchronized object statement block. The key idea here is that all the statements inside those curly braces become part of the synchronized block. And importantly, the object you specify in parentheses acts as the lock, meaning it controls access to that critical section. This allows multiple threads to coordinate their work more precisely, locking only the necessary parts of the code. Understanding this helps us write thread-safe code that's both efficient and clear, tying back to our overall goal of effective concurrency control in Java. Now let's look at how Java supports synchronization with an example. In this code, we have two synchronized blocks that are associated with the same lock, which is the instance object itself. Notice that one block is a synchronized block explicitly locking on this, and the other is a synchronized method. Both are linked to the same lock, meaning they can't run at the same time. So block 1 will never execute simultaneously with block 2. This illustrates how Java ensures that critical sections of code are executed in a thread-safe manner, preventing race conditions and data inconsistencies, and it ties back to our overall theme of managing concurrency effectively. Let's talk about synchronizing threads in Java. Java uses a concept called the monitor to manage mutual exclusion and synchronization between threads. This means that when one thread is executing a synchronized method or statement, other threads are prevented from entering that critical section, ensuring data consistency. These synchronized methods or statements guarantee mutual exclusion, which is crucial when threads share resources. However, mutual exclusion can sometimes cause a thread to get stuck if the condition it's waiting for isn't met. That's where monitors come into play. They allow a thread to wait until a specific state changes. Once the condition is satisfied, the thread can continue its work seamlessly. To control this coordination, Java provides methods like wait, notify, and notify all. The wait method makes a thread pause and wait for a condition to change. Meanwhile, notify and notify all are used by other threads to signal that the condition has been met, waking up waiting threads. This mechanism allows one thread to wait for a certain logical state, while another thread can set that state and notify the waiting threads. Understanding these concepts is key to writing robust, thread-safe Java applications and ensuring that threads coordinate efficiently without deadlocks or race conditions. Now, let's talk about the important points of the synchronized keyword in Java. The synchronized keyword is used to ensure mutual exclusive access to a shared resource when multiple threads are involved. Essentially, it helps prevent race conditions by making sure that only one thread can execute a synchronized method or block at a time when they require the same lock. Whenever a thread enters a synchronized method or block, it acquires a lock, and when it exits, it releases that lock. This locking mechanism is fundamental for maintaining thread safety in concurrent programming. However, a key point to remember is that Java's synchronized keyword does not allow concurrent read access. If multiple threads need to read data simultaneously, synchronized can become a bottleneck. For such scenarios, Java provides alternatives like the Java util, concurrent, locks. Reentrant lock, which allows more flexible control, including concurrent reads. Another important aspect is that using synchronized can incur a performance cost. Locking and unlocking are not free operations. They add overhead, which can impact the efficiency of your application. It's also worth noting that you cannot directly apply the synchronized keyword to variables, only to methods or blocks. And similarly, the volatile keyword, which is used for variables, cannot be applied to methods. Finally, there are some key methods related to synchronization that are inherited from the object class: wait, notify, and notify all. These are essential for thread communication, allowing threads to pause and resume execution based on certain conditions. So, understanding these points helps us use synchronization effectively and avoid common pitfalls in multi-threaded programming.